This is the fourth physics lab, and it is about an oscillating mass. In it, we'll be gathering position data about a mass on an oscillating spring. We will be comparing experimentally observed and model-predicted positions and predict energy changes as well. We'll be using Newton's second law and the energy principle, and our results were that the computational model predicts the total energy to be zero, the y position is underestimated, and the x position becomes overestimated the longer the simulation runs for. So in Tracker, our video is at 10.53 frames per second, and our origin is aligned with the attachment point of the spring, and the spring's length is to be 0.7 meters. The final runtime ends up being 9.497 seconds, and positive y direction is in the upwards direction. For a computational model, we got the mass, spring constant, and relaxed length of the spring from the pre-lecture videos, and the initial velocity and position, total time were all taken from the Tracker video, and the system is assumed to be the Earth, spring, and mass. Here we have just the formulas for each segment. This is kinetic energy, gravitational potential energy, and spring potential energy. This is total energy. All of this first round of calculations is defined as the initials of the system. Total force is calculated through adding each component together, so gravitational force and then spring force. The update velocity formula is taken from Newton's second formula, and the update position formula is similarly derived from Newton's second law. Again, this is calculating the finals for the spring components and the energies, and the delta versions are each going to be final minus initial. So when we run the program, we end up seeing that our total energy is going to be 0, and then this red ball is the observed position, while the blue ball is the computational position, or the computed position. The reason why this movement is so jerky is partly due to the jumps in time per frame. And then here we can see that the x position is slightly slower than the original. So it slightly underestimates the speed of the movement in that sense. And then the y position underestimates it because it doesn't go as low as the observed does. I would say that the energy principle was satisfied, as since the Earth is included in the system, there is no visible change in position on the Earth, therefore there is no work. And in our computational model, total energy is still 0. Spring potential and gravitational potential energy both oscillate opposite to each other, so they cancel each other out, and then within them, kinetic energy also oscillates, and that ends up canceling itself out within each bound. So total energy is still 0, which lines up with work being 0. For the oscillation periods, they were different in the x and y directions. This is just my work. And so the x direction is different due to the force of gravity, and the y direction is due to the spring constant. The spring constant wants to push or pull, which ends up mainly affecting the y direction, and the gravitational force has an x component once the mass is released that keeps it oscillating. If I were to make changes to this experiment in the future, I would put a little line of red tape around the mass on the spring so that when I am doing a Tracker, it's easier for me to find the center of mass and to make the points more consistent. And going back to this graph as well, as you can see, the discrepancy grows larger, so I would try to fix that if I could by refining some of the code.